Welcome student, PCH 4802 Unit 4. We are going to discuss today synthesis of unsaturated or aromatic heterocyclic compound. I am Dr. Devanga Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. First, let's begin this unit with introduction. The heterocyclic compounds are cyclic compounds containing heteroatoms like nitrogen, oxygen, sulfur into it. The heterocyclic compounds can be saturated as well as unsaturated, and we already discussed the synthesis of saturated heterocyclic compound 3-membered, 4-membered, 5-membered and 6-membered. Here we are going to discuss regarding the unsaturated compound, and in a mostly unsaturated compound we have more example for aromatic heterocyclic compound as well. The unsaturated heterocyclic compound contains double bonds and are generally aromatic in nature, and therefore this either you can say unsaturated heterocyclic compounds or aromatic heterocyclic compounds, both would be similar. This unsaturated heterocyclic compound generally involves unstrained 5-membered and 6-membered rings, which include pyrrole, furan, thiophene, pyridine. This kind of ring would be there. Another large class of unsaturated heterocycles are fused to benzene rings, which for pyridine, thiophene, pyrrole and furan or we can include quinoline, benz-thiophene, indole and benz-furan respectively. Unsaturated heterocycles have many applications. We have the example: pyridine is used as a solvent, a waterproofing agent, a rubber additive, an alcoholic dinutrient, etc. Furan has commercial application as a precursor in synthesis of tetrahydrofuran, which is useful solvent as well. Unsaturated heterocycles occurs in many natural compounds and shows pharmaceutical applications. We have the example as cladribine and pentostatin drugs are used to treat hairy cell leukemia and multiple sclerosis. These are the example of these two, cladribine and pentostatin. These two drugs are used to treat hairy cell leukemia and multiple sclerosis, which includes this heterocyclic compound either in the fused state or in a separate form. Let's begin this with synthesis of 5-membered unsaturated heterocyclic ring, and among them the first example is synthesis of 2,5-dimethylfuran. The synthesis of furan can be carried out by cyclization of 1,4-diketone in presence of an acid. The retrosynthetic analysis, that means disconnection. Retrosynthetic analysis of 2,5-dimethylfuran, the disconnection approach shows that the compound 1, here we are going to brand it by number not by name, can be synthesized by hexane 2,5-dione, that is structure 2. Further, the disconnection of compound 2 shows that 1-chloropropane 2,1 and ethyl 3-oxobutanoate, that is structure 4, are the starting reagent for this compound. Here is the retrosynthetic analysis. Here you can see from heteroatom you can put a wiggly line over here or here. So this is called a double die connection, CO disconnection, that is put on incline arrow. So here you need to put wiggly line. By mistake it is not there, but you need to put here wiggly line so that you can show that it is CO disconnection, and that is going to give us this dione, and that dione where we are going to put wiggly line over here. So C disconnection would be there, and that is 1,4-di-CO disconnection. So we're going to get these two synthetic equivalent, that is 1-chloropropane 2,1, that is this one, and ethyl 3-oxobutanoate, that is structure 4. So these two synthetic equivalent will going to obtain to synthesize this 2,5-dimethylfuran. Now here the synthesis of 2,5-dimethylfuran structure 1 is given. The target molecule is synthesized from the simple and easily available starting material, that is 1-chloropropane-2-1, and that is structure 3, and explained in 3 steps. In the 3 step we are going to show the synthesis of this 2,5-dimethylfuran. Step 1 is in the presence of a base 1-chloropropane-2-ol and the ethyl 3-oxobutanoate. They are going to react in presence of base to give ethyl 2-acetyl 4-oxopentanoate, that is structure 5. And then in step 2, decarboxylation take place on heating compound 5 in presence of acid to give structure 6. Then in step 3, addition of enol oxygen to carbonyl group leads to the cyclization of structure 6 to give compound 7, followed by elimination of water to give 2,5-dimethylfuran, that is our target molecule. So these 3 steps we have here. So we have the starting material, we need to react them, and we're going to get this dione. Then it is treated with acid hydrolysis followed by decarboxylation. We're going to get this, and on cyclization we're going to get this derivative, and on dehydration we're going to get our target molecule. Now synthesis of ethyl 2,5-dimethyl 1H-pyrrole 3-carboxylate. The pyrroles can be synthesized by Paul-Knorr synthesis, in which ammonia or a primary amine react with a 1,4-dicarbonyl compound. Here ammonia or a primary amine is the source of nitrogen, and 1,4-dicarbonyl compound provides the required carbons in the ring structure. The retrosynthetic analysis of ethyl 2,5-dimethyl 1H-pyrrole 3-carboxylate, disconnecting both carbon-nitrogen bonds of a pyrrole system, that is a ring system. So always the ring system can be disconnected by the hetero element present in the compound ethyl 1,2,5-dimethyl 1H-pyrrole 3-carboxylate gives 1,4-dicarbonyl compound, that is structure 9, and ammonia, that is structure 10. The disconnection approach for 1,5-dicarbonyl compound gives ethyl 3-oxobutanoate, that is structure 11, and 1-chloropropane-2-1, that is structure 12, as the possible starting material. So here you can see from heteroatom 2 wiggly line is placed, so it is CN disconnection. You need to write CN disconnection over here. That will going to give us this dione, and that will going to disconnect it from this. So wiggly line is shown over here. When you disconnect this one, we are going to get ammonia from this, and this another synthetic equivalent which is disconnected, we are going to get ester and this chloro derivative, acid chloride. Now here the synthesis is given. The target molecule is synthesized from simple and easily available starting material as ethyl 3-oxobutanoate and ammonia, and explained in 5 steps. The step 1, reaction between ethyl 3-oxobutanoate, that is structure 11, and ammonia gives the corresponding amine. Then in step 2, will the compound 14, that is a amine, displace the halide of 1-chloropropane-2-1 to give structure 15. Then in step 3, the lone pair of amine in the compound 15 attacks the carbonyl group to give cyclized compound 16. Then in step 4, the compound 16 loses a proton to give a double bond, and shifting to electrons neutralize the positive charge on nitrogen to give structure 17. And in step 5, finally compound 17 eliminates water to give ethyl 2,5-dimethyl 1H-pyrrole 3-carboxylate, our target molecule. You can see the synthesis over here. Structure 11, that is the ester, and the amine will going to treat on condensation. It will lose water molecule and give the structure 10, that is amine, secondary amine, and it has the what we can say isomerized compound 14. Then the 14 which have a amine, primary amine group, which have free lone pair electron shifted over here. So the pi electron will shift it over there, and we're going to get this ester group. Now on cyclization we're going to get this derivative, and then on dehydration we're going to get our target molecule. Now another synthesis is the synthesis of 2-methyl-5-phenyl thiophene. This is sulfur containing heterocyclic compound. Thiophene system can be synthesized by Paul-Knorr synthesis by reacting 1,4-dicarbonyl compound with a source of sulfur. The retrosynthetic analysis is given over here. Disconnecting both carbon-sulfur bond gives structure 19, which is synthesized by the reaction of 1,4-dicarbonyl compound with source of sulfur. Here you can see that this compound is disconnected from the heteroatom. Already I have said that the aromatic compound which contain hetero element, then the disconnection will be or wiggly line can be placed near to the hetero element, and we're going to get this dithio compound, that is compound 19, and it will going to give us dione and the source of sulfur, that is phosphorus sulfide. Now here is the synthesis. The target molecule is synthesized from 1,4-diketo compound and phosphorus pentasulfide. The synthesis can be explained in two steps. Step 1 include the phosphorus pentasulfide, that is structure 21, react with a 1-phenyl pentane 1,4-dione to give structure 19, and in step 2 the structure 19 cyclized to give intermediate 23, which eliminate the hydrogen sulfide to give 2-methyl-5-phenyl thiophene. That is our target molecule, structure 18. So here we have the dione treated with this sulfur source, and it will going to give us this disulfide, and then we're going to take this on cyclization. This is the resonating structure, and then on cyclization it will going to give us our thiophene derivative. Well, next synthesis of 6-membered unsaturated heterocyclic compound. After 5-membered, we have 6-membered unsaturated heterocyclic compounds, which include pyridine, quinoline, isoquinoline, etc. We have here the synthesis of 2,6-dimethylpyridine. The retrosynthetic analysis is given over here. The general disconnection reveals that the pyridine can be synthesized by reaction of 1,5-dicarbonyl compound with hydroxylamine. Here is the retrosynthetic analysis. 2 wiggly line placed near the hetero element. So 2CN disconnection would be there, gives dione, and this as a synthetic equivalent. On functional group interconversion, we're going to get this dione, and we'll put a wiggly line. That means this unsaturation is removed over here on functional group interconversion, and we're going to get 1,5-dico disconnection. We're going to give these two synthones. Now synthesis of 2,6-dimethylpyridine. Step 1, I have 10,2,6-dione, that is structure 13, reacts with hydroxylamine to give structure 31. And in step 2, lone pairs of nitrogen in compound 31 attacks carbonyl group to form cyclic compound 32. And in step 3, elimination of 3 molecules of water gives 2,6-dimethylpyridine, that is structure 24. Now here it is, this dione treated with the NH2OH will going to give us this derivative, structure 31. On cyclization it will going to give us this, and on dehydration we are going to get our target molecule. Now synthesis of quinoline. Quinoline can also be considered as benzofused alpha beta unsaturated imine. The retrosynthetic analysis of quinoline disconnection approach suggests that the imine nucleus may be obtained from corresponding amine, and alpha beta unsaturated carbonyl compound. So here we'll put two wiggly line to disconnect this fused ring, and we're going to get these two synthetic equivalents. Now the substituted quinoline can be synthesized by scrub synthesis by heating substituted aniline and glycerol in presence of an acid and an oxidizing agent. In step 1, glycerol on dehydration gives acrolein, that is structure 35, to which aniline adds in a conjugate fashion to give the N-substituted compound 36. In step 2, the N-substituted compound 36 undergo acid catalyzed cyclization to give 1,2-dihydroquinoline, that is structure 37. And in step 3, the 1,2-dihydroquinoline, that is structure 37, is dehydrogenated by oxidizing agent, that is nitrobenzene phenyl nitrite, to give a substituted quinoline, that is structure 33, that is our target molecule. Here is the synthesis. We have primary amine treated with this. We are going to give this derivative. On deprotonation, we are going to get this, and then cyclization will going to give us fused ring. On dehydration, it will going to give this one. On treating with pH NH2, we are going to get the target molecule. The unsaturated heterocyclic compound possessing two heteroatoms now are biologically active, synthetically useful, and important heterocycles having a wide role in medicinal chemistry. We have here the synthesis of 3,4-dimethyl 4H isoxazole 5,1. The retrosynthetic analysis of this target molecule 38, disconnection of the isoxazolene, the 38 at the heteroatoms gives well-known fragments beta ketoester 2-methyl-3-oxobutyric acid and ethyl ester 39 and hydroxylamine 40. So here this is two hetero elements are there, and after these two hetero element we put two wiggly line. So CNCO double disconnection would be there, and it will going to give us this synthetic equivalents. Now synthesis of 3-methyl-4H isoxazole 5,1, one step reaction it is, and in this case the ethyl 2-methyl-3-oxobutanoate, that is structure 39, reacts with hydroxylamine, that is structure 40, to give 3,4-dimethyl isoxazole 5,4H1 38 molecule, target molecule. So very simple reaction it would be. Synthesis of 5-methyl-2,4-dihydropyrrole 3,1. Retrosynthetic analysis of this compound that shows that the pyrazole 5-methyl-2,4-dihydropyrazole 3,1 can be, that is structure 41, can be obtained from beta ketoester for structure 42 and hydrazine, that is structure 43. So here double 2 heteroatom would be there. Secondary nitrogen enters in nitrogen, and then after two wiggly line is placed, so C and double disconnection will going to gives us the starting material. Now synthesis of 5-methyl-2,4-dihydropyrazole 3-on. This synthesis of 5-methyl-2,4-dihydropyrazole 3-on, that is structure 41, is explained in two steps. In step 1, ethyl 3-oxobutanoate, that is structure 42, react with hydrazine, that is structure 43, to give structure 44, eliminating the bottom molecule. And in step 2, the compound 44 cyclized to give 5-methyl-2,4-dihydro-3H pyrazole 3-on. So here ester is going to react with hydrazine, one water molecule depart, we are going to get this. On cyclization, it will going to gives us this target molecule, structure 41. Now unsaturated heterocyclic compound contains a double bond and are generally aromatic in nature. We have the example pyrrole, furan, thiophene, pyridine, etc. So after studying this lecture, we are going to get this summary. The synthesis of furan can be carried out by acidic cyclization of 1,4-diketone. Pyrrole can be synthesized by Palmer synthesis, in which ammonia or a primary amine react with a 1,4-dicarbonyl compound. Thiophene system can be synthesized by Palmer synthesis by reacting 1,4-dicarbonyl compound with a source of sulfur. The disconnection approach reveals that the pyridine can be synthesized by reaction of 1,5-dicarbonyl compound with hydroxylamine, and the substituted quinoline can be synthesized by scrap synthesis by heating substituted aniline and glycerol in presence of an acid and oxidizing agent. The synthesis of 3,4-dimethyl 4H isoxazole 1,5,1 can be achieved from beta keto ester to methyl 3 oxobutyric acid, ethyl ester and hydroxylamine. So this is enough from my end. Hope you have taken interest in this retrosynthetic analysis of 5 and 6 membered unsaturated aromatic compound. If you have any question, doubts, please feel free to ask anything. Asking question is a beautiful way to gain knowledge. Thank you.